Hi everyone, welcome to Unit 7 of online course on probability distributions. So far we have discussed binomial distribution and the definition of binomial distribution, how we are calculating mean, variance, other moments of the binomial distribution, etc. And in this module, we are going to discuss generating functions of binomial random variable, especially probability generating function, moment generating function, cumulative generating function, etc. And how this moment generating function or cumulative generating functions are using for calculating moments of the binomial distribution. First, we consider probability generating function. What do you mean by probability generating function? Probability generating function is actually a function which is generating probabilities corresponding to the random variable. And the definition of probability generative function is, let x be a discrete random variable having positive values, non-negative integer values 0, 1, 2, etc. Then the probability generative function is defined as expectation of s power x. Expectation of s power x, this is our probability generative function. That means probability generative function is equal to expectation of s power x, where that is obtained by summation over x, s power x f x for all s belongs to a real number system, provided this sum is absolutely convergent. If it is convergent, then that sum is called the probability generative function. And the advantage of this function is, actually we are generating probabilities corresponding to different values of the random variable. That is, the probability generative function gets its name because the power series can be expanded or differentiated to reveal the individual probabilities of the random variable. Thus, if we have the probability generative function like this, and we know that is sigma over x, some s power x f x, and that can be expanded like this. When x is equal to 0, when x is equal to 0, the value is equal to f of 0. When x is equal to 1, the value is as f of 1. X is equal to s square f of 2 plus etc. So that means these are the f of x values are the probability values. And so what is f of x from the infinite series? F of x is from the infinite series you can find the f of x by identifying the values corresponding to s, s square, etc., the coefficients of that. So we can generate the probabilities f of x of the distribution from the probability generative function, but this is generally a tedious work and is not often an efficient way of calculating probabilities. So corresponding to binomial distribution, what will be the probability generative function? We are finding the probability generating function of binomial random variable. By definition, we have, if x is a binomial random variable, suppose x is a binomial random variable with the parameter n and p. Suppose x is a binomial random variable with the parameter n and p, then our f of x, we have obtained the value of f of x as n c x p power x q power n minus x, where x is equal to 0, 1, 2, etc., and p plus q is equal to 1. So this is our binomial probability mass function. So come to the definition of the probability generative function. So p of x, p of s, that is our probability generative function, that is expectation of s power x, and by definition this is sigma over x, s power x f of x. Substituting the f of x here, we have this is from x is equal to 0 to n, sigma over x is equal to 0 to n, s power x, ncx, p power x, q power n minus x. You can see that this s power x and p power x, you combine those two factors, and combining you will get the expression ncx ps power x q power n minus x. Earlier we have the sigma ncx p power x q power n minus x, that is sum of binomial probabilities. Earlier we obtained this value as 1, and that is equal to p plus q all power n. This is a result we have already discussed. So, using this concept, this sigma over x 0 to n ncx p s power x q power n minus x is equal to, instead of p we have ps. So, q plus ps all power n. So, for a binomial random variable with the parameters n and p, we can have the value of the probability generative function using the definition of probability generative function, and simplifying the quantity is equal to q plus ps all power n. So, remember, for a binomial probability binomial probability density function, the probability generative function is equal to q plus ps all power n. And now we are moving to deriving the probable moment generative function of the binomial random variable. And by definition of moment generative function, we have the moment generative function. It is actually expectation of e power tx. This is the moment generative function. And since it is a discrete random variable, that the value is equal to sigma over x e power tx fx. So, moment generative function of a random variable is obtained, discrete random variable is obtained by summation over x e power tx into probability mass function. And we are going to derive the moment generative function of binomial random variable. Suppose x is a binomial random variable with the parameters n and p. Then we know the f of x that is equal. So, mxt is equal to expectation of e power tx. So, this is sigma over x is equal to 0 to n e power tx ncx p power x q power n minus x. Because f of x is a binomial random variable, if x is a binomial random variable, we have the f of x, that is ncx p power x q power n minus x. So, substitute f of x here, and this is our moment generative function. As we have considered in the case of the probability generative function, we derive the probability generative function by combining the factors s power x and p power x. Similarly, here also you just look, this is e power tx and this is p power x. So, these two factors are combined together. These two factors are combining, that means e power tx into p power x is combining. You have e power t into p, that is p e power t, you can write, this is all power x. So, when you are combining e power tx and p power x, this is the expression. You substitute that quantity here. So, sigma over x, x is equal to 0 to n, ncx p e power tx q power n minus x. Again use the result, that ncx p power x q power n minus x, we know this is equal to q plus p all power n. This is from 0 to n. So, using that expression, this result, you just apply this result here. You have NCX P e power t or power x q power n minus x, that is q plus, instead of p we have the p e power t. So, q plus p e power t or power n. So, remember, for the moment generative function, for the binomial random variable x, suppose x is a binomial random variable with the parameters n and p, the moment generative function is equal to q plus p e power t or power n. So, this is the moment generative function of the binomial random variable. So, for example, suppose x is a binomial random variable with a parameter, suppose 5 and 1 by 3. Suppose x is a binomial random variable with n is equal to 5 and p is equal to 1 by 3. So, the moment generative function from the expression, the moment generative function of this particular random variable can be derived or can be obtained as q. What is q here? Q is equal to 1 minus p, that is 1 minus 1 by 3, that is 2 by 3. So, this is 2 by 3 plus p, that is 1 by 3, e power t or power n, that is n is here 5. So, for this particular random variable, the expression for the moment generative function is 2 divided by 3 plus 1 by 3 e power t or power 5. So, similarly, you can find the moment generative function of any binomial random variable if the parameters n and p are known. And we know the way in which we are finding the moments of distribution using the moment generative function. Suppose you have the moment generative function mxt, then you can derive the moments of the moment random variable using the moment generative function either by expanding the moment generative function in power series of t and finding the coefficient of t power r divided by r factorial. That is, suppose you are given mxt, this is equal to expectation of e power tx, our definition is this one. So, this is equal to expectation of 1 plus tx divided by 1 factorial plus tx the all square divided by 2 factorial plus etc. tx power r divided by r factorial plus etc. using the expansion of e power tx. Taking expectation, you have this is equal to expectation of 1, that is 1 itself, and t by 1 factorial expectation of x plus t square divided by 2 factorial expectation of x square plus etc. general term t power r divided by r factorial expectation of x power r plus etc. So, when we are considering the moment generative function, by definition it is expectation of e power tx. Using the expansion of e power tx, you can write this expression as expectation of 1 plus tx divided by 1 factorial plus tx the all square divided by 2 factorial plus etc. up to tx power r divided by r factorial plus etc. And taking expectation for each term, you have expectation of 1, that is 1 itself, and expectation of tx divided by 1 factorial, that is t by 1 factorial expectation of x plus t square divided by 2 factorial expectation of x square plus etc. From this expansion, what result we are getting? The result is, suppose, and this is actually again we can write this is 1 plus t divided by 1 factorial. We know expectation of x can be written by mu 1 dash, and this is t square divided by 2 factorial mu 2 dash plus generally t power r day by r factorial mu r dash plus etc., where mu r dash, that is rth arbitrary moment, is nothing but expectation of x power r. From this, what result we are getting? Actually, we are getting that if you are expanding the moment generative function as a power series of t and identifying the coefficient of t power r divided by r factorial, that is nothing but our mu r dash. See, the coefficient of mu r dash is t power r divided by r factorial. Coefficient of mu 2 dash is t square divided by 2 factorial. Coefficient of mu 1 dash is t divided by 1 factorial, etc. So, generally we can write mu r dash, that is the rth arbitrary moment, is nothing but the coefficient of t power r divided by r factorial in the expansion of moment generative function as a power series of t. So, if it is possible to expand the moment generative function as a power series of t, then you find the coefficient of t power r divided by r factorial, that is our mu r dash. So, you can find the moment generative function. See, for the binomial random variable, we have derived that moment generative function mxt is equal to q plus p e power t all power n. This is our moment generative function. If you expand the moment generative function and find the coefficient of t power r divided by r factorial, then that is our rth arbitrary moment. But in order to find the arbitrary moments of binomial distribution using the moment generative function, we are utilizing the second method, which is the second method is nothing but earlier we have the moment generative function mxt we have obtained as t divided by 1 factorial mu 1 dash plus t square divided by 2 factorial mu 2 dash plus etc. R plus 1th term t power r divided by r factorial mu r dash plus etc. Suppose we are differentiating this moment generative function with respect to t, that is, you are differentiating the moment generative function with respect to t. You can see this is equal to, this is mu 1 dash plus 2t divided by 2 factorial mu 2 dash plus etc. So, when you are changing t is equal to 0 in this expression, that is derivative of the moment generative function when t is equal to 0, this value is equal to mu 1 dash plus all other factors consisting of t factors. So, when t is equal to 0, all other factors become 0. So, that is nothing but our mu 1 dash. So, that is, we can find the moments of the distribution using the moment generative function in another way, that is, if the function is differentiable, you differentiate the function, moment generative function with respect to t and put t is equal to 0, you will get the first arbitrary moment. Continuing this procedure, that is, you differentiate the moment generative function 2 times, that is second derivative you find, and put t is equal to 0, you will get mu 2 dash, or generally we have mu r dash is nothing but the derivative of the moment generative function, rth derivative of the moment generative function with respect to t when t is equal to 0. So, when you are given the moment generative function, there are two ways by which we can find the rth arbitrary moment. That is either differentiating the moment generative function with respect to t and put t is equal to 0, or you find the coefficient of t power r divided by r factorial in the expansion of mxt. So, these two methods can be applied to find the arbitrary moments. Sometimes the expansion is simple, then you adopt that method and find the coefficient of t power r divided by a factorial. Sometimes differentiation method is simple. If the function is differentiable, then you find the rth derivative and put t is equal to 0, you will get the arbitrary moments. And in the case of binomial distribution, see, this is more convenient for us for finding the rth arbitrary moment. Mu r dash is obtained by differentiating the moment generative function with respect to t and put t is equal to 0. Earlier we have the mxt, we obtained the mxt as q plus p e power t all power n. This is our moment generative function. So, suppose you are differentiating that moment generative function with respect to t, d mxt divided by dt. When we are differentiating, the result is n into q plus p e power t all power n minus 1 into p e power t, because this is a function of t. So, you differentiating, you will get n into q plus p e power t all power n minus 1 into the derivative of q plus p e raised to t, that is the derivative of p e raised to t is p e raised to t itself. And when t is equal to 0, what will be the value of the derivative? Derivative of moment generative function is equal to n into q plus p e power 0 all power n into p e power 0. That is, you change t is equal to 0. The expression now reduces to n into, this is q plus p e power 0 is 1. So, this is q plus p, that is q plus p is equal to 1. So, this is 1 into p again e power 0 1. So, this is equal to np. So, this value already we have derived using the usual method of finding the first moment expectation of x. Here what we are establishing, how we can find the arbitrary moments, that is mean or the second arbitrary moment me2 dash and hence the variance etc., using the moment generative function. That is, you differentiate the moment generative function with respect to t and put t is equal to 0, the first derivative gives us the mu1 dash, and again you find the second derivative. This is our function, the first derivative. You differentiate that function again, you will get the second derivative and put t is equal to 0, you will get the mu2 dash. Similarly, you can find all arbitrary moments using the moment generative function. So, that is the advantage of finding suppose the moment generative function is available to you, that is for a binomial random variable. Suppose the moment generative function is available, we are in a position to find the mean or variance or any arbitrary moments using the moment generative function without getting the probability mass function or without doing the exercise in the usual way. So, that is the advantage of obtaining the moment generative function. Second, next generative function is cumulative generative function. So, actually cumulative generative function is a function that is defined in terms of the moment generative function. That is, we have suppose we have the moment generative function is available to you, then the cumulative generative function kappa xt, that is the notation we are using, the kappa xt is equal to logarithm of the moment generative function. That is the definition of the cumulative generative function. So, for the binomial random variable already we have the moment generative function we obtained mxt. that is q plus p e power t all power n. That is our moment generative function. So, take the logarithm of that function. This we have the log mxt you are calculating when you are finding the logarithm of the moment generative function. This reduces to n log q plus p e power t. So, for a binomial random variable or for a binomial distribution with the parameters n and p, the moment generative function is n logarithm of q plus p e power t. And what is the advantage of knowing the moment generative function? We can find the cumulants, and the cumulants, the coefficient, you can find the cumulants of the random variable if we have the value of the moment generative function. As in the case of the moment generative function, here also you can find the cumulants either by finding the coefficient of t power r divided by r factorial in the expansion of moment generative function, that is our rth cumulant, and that is denoted by kappa r. So, kappa r, that is our rth cumulant, that is obtained by you expand the moment generative function as a power series of t if it is possible, and to find the coefficient of t power r divided by r factorial, then that are the values of the cumulants. Or as in the case of the moment generative function, here also you can find the cumulants by finding the derivatives of the cumulant generative function. That is, if you are finding the rth derivative of the cumulant generative function and put t is equal to 0, you will get the rth cumulant, and that is our. So, there are two different ways of finding the cumulants. That is, either you expand the cumulant generative function and find the coefficient of t power r divided by r factorial, or you find the rth derivative of the cumulant generative function and put t is equal to 0, you have the cumulants, rth cumulant. And if the cumulants are obtained, you know the simple relationship between cumulants and moments are this one. Kappa 1 is our expectation of x, kappa 2 our variance of the random variable, kappa 3 is our third central moment, kappa 4 our mu 4 minus 3 mu 2 the whole square. This relationship already we have established in the preliminary chapters of the moments and cumulants. So, that means if the cumulants are available, you can find the mean, you can find the variance, you can find the third central moment directly. So, in the case of the binomial random variable, you can have the cumulants values are like this. Coefficient of C, that is our kappa x t, already we have obtained as n logarithm of q plus p e power t. This is our cumulant generative function. And if we are following the first method, that is you expand the cumulant generative function as a power series of t, you can expand this. This is actually n logarithm of q plus p e power t, and suppose you are expanding e power t, this is 1 plus t divided by 1 factorial, t square divided by 2 factorial plus etc. So, when we have the kappa x t is equal to n logarithm of q plus p e power t, and that is equal to n logarithm of q plus p, you expand e power t is this one. Again that is simplified, you have n logarithm of q plus p plus p t divided by 1 factorial plus p t square divided by 2 factorial plus etc. And that is n logarithm of q plus p, this is our 1. So, 1 plus p t divided by 1 factorial plus p t square divided by 2 factorial plus etc. So, this is our cumulant generative function, that is cumulant generative function is equal to n logarithm of 1 plus p t by 1 factorial plus p t square divided by 2 factorial plus etc. And this is logarithm of 1 plus x. Logarithm of 1 plus x you can expand. So, that means x minus x square by 2 plus x cubed by 3 etc. When you are expanding logarithm of 1 plus x, this is the expression. So, using that expansion, just note this is equal to n log 1 plus x. This is our x. So, n x at n into p t divided by 1 factorial plus p t square divided by 2 factorial plus etc. That is our x minus x square by 2, that is p t divided by 1 factorial plus p t square divided by 2 factorial plus etc. the all square divided by 2 plus etc. So, from this expansion, you just note what is the coefficient of t power 1 divided by 1 factorial. That is our kappa 1. Coefficient of t power 1 divided by 1 factorial, this is our t divided by 1 factor. This is the only expression we have because this is a squaring factor. So, what is the coefficient of this one? N and p. So, coefficient of t divided by 1 factorial is np. That is our kappa. From the kappa xt expansion, if you are finding the coefficient of t divided by 1 factorial, that is our kappa 1, that is our mean, that is equal to np from this expansion. Similarly, you expand from this expanded value, you find what is the coefficient of t square divided by 2 factorial, and that is our npq. You find coefficient of t cubed by 3 factorial, that is our kappa 3, etc. So, using these values, you can find the cumulants of the binomial random variable when we are expanding the cumulant generative function. And finally, after discussing the moment generative function, we are going to establish one property of the binomial random variable, that is additive property. If you have two independent binomial random variables x and y with respective parameters n1p and n2p, then sum of the random variables x plus y follows binomial with n1 plus n2 and p. Remember, the additive property is satisfied by the binomial random variable provided the second parameter, that is probability of getting success, is common. That is, for x it is binomial with n1 and p, and y is binomial with the same p. Then if these two random variables are independent, the sum of random variables is again a binomial random variable with the parameters n1 plus n2 and p. And we can prove this property using the moment generative function technique. We know for a distribution, if the moment generative function exists, that is unique. That is, on the basis of the moment generative function, we can identify the distribution function of the random variable. And how we are going to prove this result here? That is, suppose x is a binomial random variable with the parameter n1 p and y is another binomial with the parameter n2 p, where both x and y are independent. Then if we are considering the moment generative function of x, we know this is equal to q plus p e power t all power n1. because we have already established that moment generating function of a binomial random variable with a parameter n and p as q plus p e power t all power n. Since x is a binomial random variable with a parameter n1 and p, the moment generating function is q plus p e power t all power n1. Similarly, moment generating function of y is equal to q plus p e power t all power n2. These are the moment generating function of these two binomial random variables. Now, you consider the moment generating function of MGF of the random variable x plus y, and that is m x plus y of t. Since x and y are given as independent random variables, by the property of the moment generating function, this can be written as, or this is the product of the moment generating functions of x and y. This is a property of the moment generating function. If x and y are two independent random variables, moment generating function of sum of random variables is equal to product of the moment generating function. Substitute the values. This is q plus p e power t all power n1 plus q into q plus p e power t all power n2. And combine these two factors, you can write this as q plus p e power t all power, this both are the base are same. So, this is power n1 plus n2. Just look the moment generating function. This is the moment generating function of x plus y, that is similar to the moment generating function of the form q plus p e power t all power n. Instead of n, we have this n1 plus n2. Since q plus p e power t all power n is the moment generating function of a binomial random variable, from this we can conclude that this x plus y is a binomial random variable with the parameters, this one parameter, that is n1 plus n2, and the parameter, second parameter is p. So, this is the way we are establishing additive property of binomial random variables. And you can generalize this property for n independent random variables, that is, if x and y are, instead of taking two binomial random variables, we are considering k independent binomial random variables with the parameters n1 np, n2p, n3p, etc. up to nkp. Then sum of the random variables x1 plus x2 plus etc. up to xk is again a binomial random variable with the parameters n1 plus n2 plus etc. up to nk and p. That is, suppose we have k independent binomial random variables, then sum of the binomial random variables is again a binomial with a sum of parameters. This is the generalization of the additive property. So, with this we wind up this session, and we will discuss further with regard to mod and other things in the next session. Thank you.